Good morning, students. Welcome to the mass transfer course. Today will be lecture 14. So we have covered 3 chapters. First chapter was introduction and motivation. Second chapter was molecular diffusion, and third chapter was convective mass transfer and mass transfer coefficients. In chapter 2 and chapter 3 we calculated the flux for molecular diffusion in chapter 2 and in chapter for convective flux at NA. But in both cases the mass transfer is occurring in a single phase. Okay, here if you see, we consider point 1 to point 2, and that was the homogeneous mix, a single phase. Either it was gas phase or liquid phase, or it can be solid phase. Today we will start the interphase mass transfer, that is the chapter 4. From name you understand there are 2 phases will be in contact, and this chapter is the most crucial and most conceptual chapter in mass transfer course. If we understand this chapter, then all the remaining things of mass transfer will be just application of this chapter. So let's start this interphase mass transfer. Now already I told that for separation of molecules through mass transfer, generally 2 phases are in direct contact. And already we have taken the examples. The first, let's take that removal of carbon dioxide from synthesis gas. Okay. Synthesis gas is nitrogen, hydrogen and carbon dioxide mixture. Okay, I want to remove carbon dioxide, so I use the ethanol amine by absorption process. So nitrogen, hydrogen, carbon dioxide was in gas phase, ethanol amine is liquid phase, so there is a gas liquid direct contact, and carbon dioxide diffuses from gas phase to liquid phase. So 2 phases were involved in this process. Again, another example we have taken, the separation of ethanol and water from their mixture by distillation. Distillation means liquid vapor, that is there are also 2 phases are there. Then we have taken the example of gold, extraction of gold using sodium cyanide, that is also solid liquid. 2 phases are involved. Absorption of water vapor in silica gel, that is gas solid. And we have taken the penicillin, recovery of penicillin from fermentation broth, that is a liquid phase, using butyl acetate or methyl isobutyric ketone. But these 2 liquid, this is also liquid, but they are immiscible to each other. One is aqueous phase, another is organic phase, so that penicillin will come from aqueous phase to organic phase. This was the liquid equilibrium. So whatever the practical examples we have taken, what is happening in reality, if you see, all are 2 phases are in direct contact. Actually, through single phase separation in single phase, it is economically not feasible. It is found because separation will be so low, so it is not acceptable from economic point of view. Then they tried to bring two phases are in contact, and particular one component has affinity to connected from one phase to another phase, and that gives the separation in economic way. So already we have seen this example in introduction and motivation chapter. Same thing, same examples I am taking here, but you see now what is happening. All separation processes are involved in two phases, and we have also taken that phases are gas, liquid, solid. Okay, so must take place, but absorption, gas to solid, absorption, liquid to gas, stripping, then distillation using vapor liquid equilibrium, adsorption, gas solid, solid to gas desorption, these are combined, then drying, solid to gas, solid to liquid, leaching, liquid to solid crystallization, liquid to liquid, that extraction. If you see, whatever the mass transfer processes or separation processes are these things: adsorption, stripping, distillation, adsorption, desorption, drying, leaching, crystallization. These are the separation processes, and these are typically used in industry. And all these things, if you see, always there are two phases are there. So mass transfer occurs between two phases. So when two phases will be in contact, these are direct contact, then there will be one interface, and that is called the interphase mass transfer. Now what is happening here in interphase mass transfer? Let's take example, absorption of carbon dioxide from the mixture of nitrogen, hydrogen, carbon dioxide through ethanol. So there are one phase is gas phase. Here nitrogen, so if you take this one, it has a mixture of nitrogen, hydrogen and carbon dioxide. Okay, these three molecules are in gas phase, and this is ethanol, liquid phase. This is the liquid phase, blue one. Red, this color is, let's take the gas phase. This is ethanol. So two phases are in direct contact, and this is called interphase. FAC. Okay. So this is the interphase. So what is happening here? So bulk gas flow is there, and there will be that interface, there will be the gas film thickness. Okay, this is gas film thickness. There will be one film gas, because bulk gas, then that, and this is that concentration will be there, that is the interfacial concentration. So bulk concentration to interfacial concentration, there will diffusion will take place, then it will take up the liquid, then from this is the concentration, interfacial concentration of the liquid phase, and then it is diffused through this, and this is the liquid film thickness. So if two phases are in contact, then there will be two boundary layers. One is from gas side, film thickness, okay, and another is in the liquid side. Okay, so now here carbon dioxide is diffusing from gas phase to the liquid phase. So in this way it is coming, and this is the bulk concentration of the diffusing element. Okay, so in this case there will be two boundary layers. Two boundary layers will be in direct contact, and this contact point line is called interface. Now if you see this picture in more deeper way, so this will be like this. Okay, so this is Z equal to 0, this is the interface, okay, and this dotted line, this is the liquid film, okay, and this will be your gas film. Okay, so this is your gas film and this is bulk. So gas film is this, if you can see this, okay, and this is your liquid film. Okay, now the solute is A. Okay, so if you take the hydrogen, nitrogen, carbon dioxide, okay, so if I take this is, I consider A, this is diffusing, and this is not diffusing, this will be considered B. So in this case carbon dioxide YAB, bulk concentration. Okay, so it will diffuse from gas phase to liquid phase, so there will be a high concentration, and then it will look like this in the interface, that is the concentration YAI. Okay, then concentration of, when it will come to the liquid side, just I'm coming to the liquid side, XAI. Okay, this is the concentration of A in the at the interface in the liquid side, and YAI is the concentration of A at the interface in the gas side. Okay. But if you note this, it is not that YAI equal to XAI. I will tell, I will come what in detail why it is look like. Okay, and then if it come liquid phase, then the liquid, it will diffuse from interface to this is the bulk concentration of solubility, isn't it? So mass transfer from one phase, say gas phase, okay, G phase or G phase, to another phase, say liquid phase, L phase, involves following sequential steps. The solute A is transported from the bulk of the gas phase to the gas liquid interface. So there is this step 1. The second is the solute A is picked up or absorbed by the liquid phase L at the gas liquid interface. So then that's the XI, YI, it is converting to XI. Then the thing is that the absorbed solute is transported from the interface to the bulk of the liquid. So interface mass transfer is nothing but when two phases are in contact. When two phases will be in contact, there will be two boundary layers. One will be from G phase side, one will be for the L side. Steps A, B, C. So there are 3 steps. This is the diffusion, then that absorption in this case of our picked up, and then also diffusion in the liquid. Steps A to C of the above are facilitated by turbulence in the fluid mechanics. What is the interface mean? Interface means the geometrical plane or surface of contact between two phases. Okay, so if Z, let's take this is Z equal to 0, Now if Z equal to 0 plus, then it will be XAI concentration, and if Z equal to 0 minus limit, okay, then it will be the XYAI. Okay. Now there is one concept is there, that is film theory. What they are telling, so here I am same thing I am defining in this is in terms of partial pressure, gas phase, and this is liquid phase CAI. I can convert this way also. So this is main liquid, means bulk liquid, this is bulk gas, this is liquid film, this is gas film, okay. And at the interface we will assume that the interface, this what is the concentration of gas side and concentration of the liquid side, it will be in equilibrium. Okay. At interface, assume that at the interface and Henry law with constant value of Henry's constant, this will be active. Or you can apply here Henry law, or you can apply here the Raoult's law, whatever, but at the interface this will be at equilibrium. Okay. Now why it will be equilibrium? Because I am telling that interfacial concentration YA and XI mean, okay, what does it mean? Limit YI Z tends to 0 minus, then it is YI, and Z tends to 0 plus, limit XA, that is XY. So interface is nothing but a very thin line, that is conceptual limit. So it is practically at the interface, it does not have any resistance. You understand the concept? Means Z equal to 0, limit Z 0 minus, okay, then it will be YI, Z limit Z 0 plus, this is XI. So it is a limit concept. Limit concept, it is the imaginary line and almost zero thickness. If it is a 0 thickness, I cannot tell it is 0, but tends to 0, limit concept. So tends to 0 means practically 0. 0 means there is, if the 0 thickness means there is no resistance. That's why that interface, that will be always in equilibrium. If there is no resistance, always it will be equilibrium. Okay. So that's why physically XYI is the mole fraction of A on the gas side of the interface, and XAI is the mole fraction of A in the liquid side of the interface. Commonly these are called interfacial concentration. In most situations involving mass transfer, we assume that equilibrium exists at the interface, that is YI XAI is equal to are in equilibrium, and this is sometimes written as that YAI equal to function of XI, that is the equilibrium relation. Okay. So equilibrium relation you have already studied in your thermodynamics, where the function Y represents the dependence of YA and XI at equilibrium. This function is also called equilibrium relation. Okay. And sometime we call this YI equal to MXI, where M is the Henry law. Okay. So because in solid and gas liquid, Henry law, Raoult's law, these are applicable, you know. So it is clear, no? So there are 3 steps. First step is bulk gas or G phase, to it is coming to the interface, then interface, that is in equilibrium condition, then YI equal to XAI, that relation is there, then diffusion of XAI to XAB. These 3 things are happening in interface mass transfer. Now, as at the interface, the solutes are in equilibrium, let's try to understand little bit equilibrium relations, gas liquid equilibrium. Already you have studied in thermodynamics 2 gas liquid equilibrium. Just I will give a little overview on this, so that whatever you have studied, it will be recapitulated. Now how will you generate the equilibrium data? Okay, let's take, I want to generate the equilibrium data, ammonia in gas mixture, means in air, and ammonia is there, and it's now ammonia is getting dissolved into the water. Because in many processes, if you have a small amount of ammonia, okay, 1%, 2%, to absorb this ammonia, water is sufficient. Ammonia will diffuse from the air mixture, air ammonia mixture to air. So for that one, I want to see that what is its equilibrium data. How will you make this? I can make a very simple experiment. If I take this type of container, okay, then I will put it here some water, okay, and there will be two valves, okay, two thing, and then I will put the air here, air ammonia mixture. Let's take, it has a 2% air ammonia mixture, 2% ammonia, 98% air. I put this one, okay. Then what will I do to bring the equilibrium? You know, you have to allow it for a long time and keeping the temperature constant, because with temperature change, that absorption, equilibrium will be different. Now if you allow sufficient time, then ammonia will dissolve from gas phase to liquid phase, means air to water, and similarly some ammonia will go there. Both process will be better, but at equilibrium, what will happen? How much will be dissolved? That much will go. Means net there won't be any dissolve of ammonia in water. If whatever dissolve is going on, same thing is going on up. That's mean that is called, it is in a dynamic equilibrium. Generally it will be in a dynamic, but why it is a equilibrium? Because after when it will come, the rate of dissolve and rate of strip off, it go when same, then with time there won't be any concentration change either in gas phase or in liquid phase. Let's check that is, then that means it reached at equilibrium. So at that time, YA star is the concentration of ammonia is the in liquid gas phase, and XI is the concentration of liquid. How will you know this? When it will reach to the equilibrium, I will take little bit sample, I will make the analysis, and I will take the gas phase from, I will make the analysis, and then it is possible to determine the concentration of ammonia in gas phase and liquid phase. So if I know this one, the gas phase, let's take, this is the gas phase concentration, liquid phase concentration, if I know, let's take this is 0.1, and gas phase, let's take 0.12. So 0.12 if you take for a particular cell, then I will get this point. Okay. So first point I got equilibrium point. Then how do I look? Then again I put some more ammonia. It means if I put more ammonia, 2% to, let's take, if I put it 5%, then again this equilibrium will be disturbed, then more ammonia will come to the liquid water phase, and after a time one new equilibrium will be reached. Then let's say that if I put more ammonia, so more ammonia will come into water, and corresponding some one ammonia will be in air, and let's take this is the second point. So two equilibrium experiments, okay. then I put some more ammonia into this one. If I put this one, then again it will take time to reach another equilibrium. Okay, and when we will take the sample, then at equilibrium I will measure the y star, x star, then let's take this is the thing. Okay, and in this way I can make these points, and then if I draw this one, this is the equilibrium. Why equilibrium line is important? Because we know mass transfer is possible up to the equilibrium. When it will reach to the equilibrium, then mass transfer is not possible, isn't it? Equilibrium means what? Then flux, net flux will be zero. That means no mass transfer will take place. So equilibrium line will tell you, okay, you can go up to this, mass transfer is possible, beyond that it is not possible. So that's why equilibrium data is very important. Okay. And at the interface, it is in a equilibrium. Means when if you change whatever yi you will change, corresponding xi will change automatically very fast, because there is no resistance. You know this one. If no resistance is there, no driving force there will no driving. If resistance is zero, then driving force will be your zero. In thermodynamics, in heat transfer also, if you see, higher temperature to lower temperature, if resistance is no there, means no insulation is there, then temperature will be same here, isn't it? So because here at the interface the resistance is zero, so there is no mass transfer. That always it will come to an equilibrium. So in this way you can make one equilibrium curve, y star minus yx at constant. Either you can do it through the experiment. Also you have studied, there are some models are there. If you know the x concentration, then what will be the y concentration, it is possible. Okay. Now let's take, this is your x star this is your y star, okay. Now let's take for this one, this line is the equilibrium curve for the moderate solute. Moderate solute means in equilibrium gas phase will be, let's take 30%, liquid fluid will be 20%, gas phase will be 60%, liquid phase will be 40%, like this. Okay, moderately. So it will be almost whatever the x value, y value will be almost same, and little bit that will be it will go like this. Now let's take the absorption of ammonia in water. Absorption ammonia in water means actually water, ammonia is highly soluble in water. If highly soluble in water means ammonia will prefer to stay in liquid phase rather than in gas phase. That means at equilibrium gas phase concentration will be low and liquid phase concentration will be high. If you see, let's take this point. If you take this point, let's take this point, any point. So here this is your xi, this is high. Let's take this is how much it will be up to 1, okay, and this will be up to also 1. Maximum mole fraction can be 1. So let's say this is xi equal to, let's take 0.8, and if you see yi equal to, let's take 0.1, xi equal to, let's take 0.8, and this is equal to 0.1, means this is yi. Isn't it? So at equilibrium, you see, if for highly soluble solute, let's say ammonia in water, then at equilibrium always the concentration is liquid phase will be much higher than the concentration in the gas phase. That means this curve will be then like this, it will be below this diagonal, and if it is a very soluble, then it can take below of this line also. Okay. So seeing this equilibrium curve, you can understand whether it is highly soluble or not, isn't it? And if you take the one very sparingly or less soluble solute means oxygen in water. You know that in air the oxygen concentration is 21%, means 0.21. Do you know what is the concentration in water? What is the concentration of oxygen in water? It is around 8 ppm. 8 ppm means 8 into 10 to the power minus 6 mole fraction. Take into, so 8 into 10 to the power minus 6, and it is 0.21, and it is 10 to. So if it is, that means concentration for less soluble solute, concentration of gas phase will be high, and concentration in liquid phase. That means if you see gas phase high, liquid, let's take this point here, this is a liquid phase, how much? This is low, and it is around 50.5, this is 0.1. Okay, and if it is very less soluble, then it curve may be like this also. Okay. So that equilibrium curve is very important, because seeing the equilibrium curve between two phases, you will understand what phenomena is going to happen. So if let's take, if we have a one equilibrium curve like this, less very soluble. So now if I want to bring oxygen to this water, will it come? It will not come, only 8 ppm at equilibrium. But if you take this one, ammonia in water, it will come. So we should use this one, ammonia. And if you use ethanolamine, the curve will be much below this. So that is more acceptable limit. So equilibrium curve is plays an important role in separation. So seeing this curve, you will understand what is going on. Okay. So generally, less soluble or sparingly soluble solute, the curve will be stiffer, and for highly soluble solute in liquid, okay, so these will be like flat. This thing you should understand, and you have to, before that you have studied the thermodynamics, now you have to apply this thermodynamics. So each data is important. Seeing this data, you will understand. You have to devise the mass transfer protocol, what way we will do. Okay. Now we know that at equilibrium means chemical potential of gas phase and liquid phase is same. Let's take mu Ig, means I means ith component gas phase and ith component, and generally at constant temperature, that fugacity of gas phase of ith component will be fugacity of that unit. And what is the fugacity of gas? Fi, yi is mole fraction, this is phi I is the fugacity of the ith component, and P is the total pressure. You know this one from your thermodynamics too. And for liquid phase, xi is mole fraction in the liquid phase, gamma I is the activity coefficient, pi sat means saturation pressure of ith component, isn't it? Now this, these are the very important parameters, okay? Fugacity coefficient for gas phase and activity coefficient for the liquid phase, isn't it? This is the generic thing, okay? Now if take the generic easy case, okay, that means if let's say both gas and liquid are ideal, okay, if gas phase is ideal, this phi I will be 1 and liquid phase gamma I will be 1. So YIP, or you can PI, okay, partial, if you product of this is partial into XI into PI sat, that is the Raoult's law. So Raoult's law is applicable for ideal cases when both gas and liquid are ideal cases. And in mass transfer, why Raoult's law is widely applied? Because in mass transfer processes, generally pressures are low, 1 atmosphere and 1.5 atmosphere like this. That's but if it is a, let's say 200 atmosphere, then it will, Raoult's law will not be applicable. Generally when pressure is low, then Raoult's law sometimes it is applicable. But for liquid this is different. And for binary system, YAP, okay, into XA PA sat or PA equal to XA P sat. So this is your Raoult's law. But keep it in mind, Raoult's law is applicable when gas and liquid both are ideal. Okay. Now if you take another case, for non-ideal gas liquid system at low concentration, then this is the case, common equation, yi phi I into p equal to xi gamma I into pi sat, ith component. So yi equal to gamma I pi sat into phi I p equal to x. Now this equal to m. Why I am telling? They are telling that for non-ideal gas liquid system, it need not to system should be the ideal. Generally it will be liquid system is generally gas system. If pressure is low, gas will be transferred, but liquid it is not like this. If pressure low high, it does not matter, because liquid system will be ideal when interaction of like molecules will be equal to interaction of the unlike molecules, which is not generally possible. So that's why telling for non-ideal gas liquid system at low concentration, that is very important. If concentration is low, then this part is almost constant, and this is called our Henry constant, and this is the Henry law. Okay, so generally actual thing is this in gas liquid system. But if both gas and liquid are ideal, then Raoult's law will be applicable, and Henry law will be applicable at low concentration. If concentration is low, then it will be this. Okay. So Henry's law is applicable at low concentration. Okay. And in general, if you have let's take 1% ammonia, you want to absorb in water, so then that's mean low concentration. So that case you can apply the Henry law, that is it. Now, so this is the equilibrium relation. Now if let's take m equal to 10, if m equal to 10, so let's take yi equal to 0.9. So 0.9 in equal to 10 Henry law, 10 into xi. So xi will be 0.09. So at equilibrium, what is, if yi equal to 0.9, xi will be 0.09, 10-fold less. And if m equal to low, let's say m equal to 0.5. Now let's take this is equal to, this is 0.9. So what will be yi? Yi will be 0.045. That's mean in this case yi will be lower, xr will be higher. If m is equal to less than 1, then yi will be lower, xi will be higher. If m equal to greater than 1, then yi will be higher, xi will be lower. Now you understand this. Now because for highly soluble, if soluble, highly soluble means what? Xi is higher. If xi is higher, then m will be low. Means less than 1 it will be, and it will be low. And when for less soluble, this is higher and this will be lower. That's mean that m will be high. Okay. So that's why if you see this at the interface, this is at equilibrium relation. So that's why yai equal to m into xi, isn't it? Now if m equal to y, then yai will be xi. But in this case, whatever the yi, xi is less. xi is means what? M equal to greater than 1, isn't it? If m greater than 1, then yi will be greater than xi. And if m less than equal to 1, then yi will be less than xi. So that's why generally yi and xi, these are not the same. Generally m is not 1. It will be either greater than 1 or less than 1. For highly soluble solute, okay, then xi will be higher. So that time for highly soluble solute, xi will be this. And for less soluble solute, this will be this. So highly soluble. And this will be happen for less soluble solute. Less means gas phase concentration will be less. Is it understandable? Keep it in mind that at the interface, what is the concentration of yi and xi? It depends on the equilibrium relation. And equilibrium, if you take the Henry law, if for highly soluble solute, generally xi will be higher than the yi. So that time, xi will be higher than this one, xi. And for less soluble, this will be lower. And if it is a 1 m equal, then it will be here. But then must generally, this will be ineffective mass transfer. There you will not get much of. So that difference must be there. Okay. Similarly, for liquid-liquid equilibrium, for the equilibrium distribution of solute A in two essentially immiscible liquid phases L and L dash as distribution law given by this is called valid, and where K, this is Ca at one liquid phase L, and this is the concentration Ca is another liquid, and L and L dash are immiscible too, and this is called the distribution coefficient. Okay, so if distribution coefficient is low, that means if it is low, then this concentration will be higher than this both are in liquid. So I will, so let's check if I want to, want to separate penicillin from water to butyl acetate, that equilibrium, that K value should be less than 1, and K value should be as low as, then it is a better. So then maximum penicillin will come to this butyl ethyl or butyl acetate. Okay. Similarly, for M, if M dash gas liquid, M dash is low, that is good. If it is, we try to keep as low as possible, but it depends on the particular system. You cannot, but you have to select the solvent in such a way so that M is low. So thank you for your attention. So today we just started our interphase mass transfer, and in interphase mass transfer we have seen two phases are in direct contact. What is the contact line? That is the interface, that is the imaginary line almost with zero thickness. That means there is no resistance is there. That means at that interface there is equilibrium exists. Okay, and equilibrium concentrations are YI and XI, and YI generally will not be the XI. It will depends on the equilibrium relation M. Okay, or for Henry's law, and for liquid system that is the K distribution. And always for better separation process, if M is low, F is low, then it will get the better separation process, and K is low, better separation process. And to understand the interface, we discuss about the equilibrium concept again, what you have studied in thermodynamics 2, where we have generate one equilibrium curve Y star X star and generic equation. From there we have seen the two equations, one is Raoult's law and another is Henry's law.